Right now, as you're watching this, 4 astronauts are further from Earth than any human being has been in 53 years. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen launched aboard Artemis II on April 1st, headed for a high lunar orbit that will take them beyond the distance record set by Apollo 13. And within 48 hours of liftoff, the sun hit them with a G2 geomagnetic storm. The KP index spiked to 6. The solar wind nearly doubled. The interplanetary magnetic field flipped southward and stayed there. They are now transiting through a region of space with no magnetospheric protection, heading deeper into the void, while 3 active sunspot regions capable of producing X-class flares are pointed directly at Earth. The probability of at least one major eruption before they get home is above 60%, and NASA has said almost nothing about it. If this has you paying attention, stay with me until the end, because this mission is just getting started, and the solar activity driving these conditions is only intensifying as we head deeper into solar maximum. Drop a comment telling me where you're watching from, and let me know, do you think NASA made the right call launching into these conditions, or should they have waited? Now, let's get into it. On April 1st, 2026, at 6:24 in the evening Eastern Time, a Space Launch System rocket lifted off from Launch Complex 39 Bravo at Kennedy Space Center. The roar of those 5 engines, the twin solid rocket boosters screaming at 2.7 million pounds of thrust each, the core stage RS-25 engines producing another 8.8 million pounds, was the most powerful controlled explosion ever conducted by humans. The rocket was 422 feet tall. The Orion spacecraft riding on top, with its heat shield and its service module and its systems for keeping 4 human beings alive, was the most advanced spacecraft ever built. The 4 astronauts inside had trained their entire careers for the moment they were experiencing right now. That shudder at ignition, that acceleration that pressed them back into their seats, that ascent that took them from the surface of the Earth and into the dark. Reed Wiseman was commanding the mission. Wiseman spent 20 years in the United States Navy, flew F-18 Hornets for the Naval Air Force, spent more than 1,000 hours as a pilot in combat operations, and then transitioned to space as one of NASA's most experienced shuttle and station commanders. Victor Glover was flying as pilot, Christina Koch was flying as mission specialist, and Jeremy Hansen was flying as mission specialist for the Canadian Space Agency. The 4 people on board were at the absolute peak of their capabilities, selected from more than 18,000 applicants across multiple countries. They had trained for years in isolation in the desert of Arizona and the plains of Texas, flying complex simulators that reproduced the system's failures and anomalies they might encounter. They had trained in neutral buoyancy pools, breathing through spacesuits while submerged, learning what it felt like to move in an environment without gravity. They had been spun in centrifuges until they had experienced forces that pressed on their bodies with multiple times their normal weight, teaching their inner ears and their hearts how to respond when they lifted off. And now, on April 1st, they were actually doing it. The public had gathered in enormous numbers to watch. More than 400,000 people lined the beaches and causeway near Kennedy Space Center. They came with cameras and blankets and lawn chairs, understanding they were witnessing something rare and profound. A human space launch, in person, is not something that crowds forget. The rumble of those engines travels through your body. The plume of rocket exhaust towers into the sky. The sight of that vehicle accelerating upward, leaving the Earth, reaching towards something that no humans had gone to in 53 years. It changes something in the observer. The footage was everywhere. News networks carried it live. The trending pages filled with reaction videos. The moment that Orion cleared the launch tower, that Orion accelerated past the speed of sound, that Orion left behind the thick atmosphere and entered the realm of thin air and then vacuum, it was broadcast to a global audience. People on social media were celebrating. Space programs were releasing official statements. The anticipation was real and collective and historically significant, humanity was, for the first time in more than half a century, sending a crewed vehicle toward deep space. And the crew was about to discover that the deep space they were entering was far more active than anyone had expected. What nobody expected to happen next came within 48 hours. A geomagnetic storm struck, not a minor one. A G2 class event, which in the modern scale of space weather sits firmly in the strong category. At 17:05 Coordinated Universal Time on April 2nd, real-time instruments pegged the KP index at 6, meaning that aurora was visible from much of the northern United States, and that the magnetosphere was being rocked by sustained, violent oscillations. The solar wind, which had been running at a quiet 435 kilometers per second when the crew departed, had jumped to around 700 kilometers per second. The BZ component, which measures the northward or southward orientation of the interplanetary magnetic field, had flipped southward and bottomed out at -16 nanoteslas. That specific condition is one of the most efficient ways to couple solar wind energy directly into Earth's magnetosphere, turning the planet's magnetic field into a seething, turbulent boundary zone. Here's where the timing becomes important. The crew, at that moment in their trajectory, was no longer cocooned in the protection that Earth's magnetosphere provides. They were already in transit, already beyond the shielding that keeps the radiation belts from reaching the surface, already in deep space in a way that humans rarely are. The original launch window, the original safety envelope, had involved a certain probability of space weather events occurring during the mission duration. NASA had issued a G1 watch before launch, meaning meteorologists at the Space Weather Prediction Center were already on alert for the possibility of stormy conditions. But this wasn't just a watch. This was a storm that actually arrived, and it arrived while they were midway between two worlds. The question that very few people in the mainstream media wanted to ask was whether that launch was delayed, reassessed, or reconsidered in light of the forecast data available in the hours before the April 1st departure. The Space Weather Prediction Center data from March 31st was clear. An active region called Region 4405 had just produced an X1.4 flare on March 30th. That same active region was still rotating toward a more Earth-facing configuration. On the morning of April 1st, the solar wind was already elevated. The KP index was elevated. Conditions were moving in the wrong direction, and the decision was made to proceed. This is not to suggest that NASA engineers made a reckless choice. The launch commit criteria for space weather are specific and publicly documented. At the moment of liftoff, conditions did not breach those formal thresholds. The geomagnetic storm that followed came within the probabilistic envelope of acceptable risk that the space program has long accepted when launching during solar activity seasons. But the corollary question sits in a slightly different space. Did the schedule pressure, the political optics of launching when promised, the momentum of a mission years in the making, influence the conversation around that decision in ways that were subtle enough to never appear in the official documentation, but real enough to matter? Did the cost overruns on Artemis, already billions of dollars above initial estimates, create a background pressure to proceed when conditions were uncertain? Did the national imperative to demonstrate that human spaceflight capability was returning to this scale influence the threshold of acceptable risk in conversations that weren't recorded? What happened next is that the sun wasn't finished. And that's where the story stops looking like routine space weather and starts looking like something else entirely. On April 2nd, at 1815 Coordinated Universal Time, an active region called Region 4404 unleashed an M3.5 flare. That's in the middle tier of solar explosions. Not as powerful as the X-class regions that are grabbing headlines, but substantial enough to be geographically significant. Within a few minutes, the coronagraphs on the SOHO satellite, which observed the sun's outer atmosphere, picked up a narrow coronal mass ejection. The ejection appeared in the Molucca Sea, two-camera feed after 1848 UTC, and the modeling from multiple forecasting centers suggested it was heading in a direction that could intercept the Earth region, or at minimum graze the outer magnetosphere. The geometry was uncertain, but the trajectory was concerning enough that updates flowed continuously through the Space Weather Prediction Center's operations room. Now, think about what an M-class flare actually does to the region around the Sun. The Sun's surface is roughly 5,700 Kelvin. The corona, the outer atmosphere that you see during a total eclipse, sits at something like 1,000,000 Kelvin or higher. The temperatures and the physics are so extreme that the normal rules of Earth physics break down. The solar plasma behaves according to the rules of magnetohydrodynamics, where magnetic fields and electrified gas become woven together in ways that can store enormous amounts of energy. When a flare erupts, what happens is that magnetic field lines that have been twisted and sheared and compressed suddenly snap. They reconnect in a new configuration, and in doing so, they release energy that was stored in the magnetic field. That energy heats the plasma around it to tens of millions of Kelvin in seconds. It accelerates electrons and protons and heavier ions to relativistic speeds. It produces radiation across the entire electromagnetic spectrum, from radio waves to X-rays to gamma rays. The light from that explosion travels outward at the speed of light. The particles follow at slightly lower speeds. The coronal mass ejection, a pocket of plasma ripped away from the solar atmosphere and hurled outward, follows at speeds that can exceed 2,000 kilometers per second. All of this happens in a region of the Sun that is roughly the size of Earth, and the energy released is equivalent to billions of nuclear weapons detonating simultaneously. That is what an M-class flare does. This M3.5 followed on the heels of something more significant. Remember that X1.4 flare from region 4405? That occurred on March 30th, and it produced what's called a Type II shockwave traveling outward from the Sun at 1,872 kilometers per second. The radiative output was intense, measuring 1,800 solar flux units at its peak, the kind of reading that makes radio blackout forecasters sit up straighter. The Type II radio burst, the signature of that shock wave as it traveled outward through the solar corona and into the solar wind, was detected by radio observatories and ham radio operators worldwide. A Type II burst means that the shock wave is strong enough and fast enough that it's actually accelerating charged particles to speeds where they emit radiation in the radio frequencies. It means ham radio operators sitting in their basements with their receiver equipment got to hear the signature of a solar eruption being broadcast across space at the speed of light. It's the sound of the Sun exploding. The coronal mass ejection associated with that flare was partial halo, meaning it expanded in multiple directions from the Sun's surface, with a substantial component aimed toward Earth. Now, consider what was happening on the solar disk at that moment. Region 4405 was still there, still rotating, still facing Earth, still capable of producing further major eruptions. Its classification was EAI, which in solar terminology means it was a large, complex, magnetically sheared region with 220 millionths of the visible solar disk covered in magnetic spots. 15 individual sunspots were counted within it. The probability of an M-class flare was estimated at 20%. The probability of an X-class flare within the next 24 hours was estimated at 5%. That doesn't sound like much until you realize the baseline rate for X flares on a quiet sun is closer to 0.5% per day. But region 4405 was not alone. Region 4404, the one that had just produced the M3.5, was itself beta-gamma in structure, meaning it had both positive and negative magnetic polarities in close proximity, which is the configuration that tends to produce instability. Region 4409 sat further west on the disk, classified as Dye, with 15 distinct spots, and a configuration that forecasters rated as carrying a 25% probability for M-class activity and 5% probability for X-class within the next 24 hours. Across all 11 active regions visible on the solar disk on April 2nd, the cumulative daily probability of an X-flare was approaching 10%. Over the 9-day duration of Artemis II, the Space Weather Prediction Center's statistical models suggested a cumulative probability of between 60 and 65% for at least one X-class flare before the mission concluded. The immediate forecast for the solar wind and geomagnetic activity was for sustained instability. SWPC issued outlooks calling for 55% probability of R1 to R2 radio blackout conditions and 20% probability of R3 conditions, which means X-class flare activity through April 5th. The discussion text in the SWPC forecast mentioned that regions 4400, 4405, and 4409 all carried significant flare potential and were being actively modeled for the next several days. The ongoing modeling suggested that regions 4400, 5, and 4409 were both rotating into more geo-effective positions, meaning the flares they produced would be aimed more directly at Earth and would have more severe effects on the magnetosphere. The CME that had already been launched from the April 1st filament eruption, a separate event from the region 4405 X flare, was being tracked and modeled to arrive sometime late on April 3rd or early on April 4th. That was expected to be the primary driver of the upcoming G2 or possibly G3 geomagnetic storm. The solar wind was already running at 656 kilometers per second and climbing. The crew of Artemis II, now well beyond Earth's magnetosphere, was being inserted into what climatologists might call an active season of severe solar weather, compounded by the fact that the regions capable of producing the most dangerous eruptions were still facing Earth and still rotating into increasingly geo-effective positions. And on the very day when the worst of these conditions were expected to arrive, April 4th, something else was happening in space. Something that had nothing to do with the sun and everything to do with how the universe sometimes arranges its coincidences in ways that make investigators deeply uncomfortable. April 4th, 2026 was going to be a significant astronomical date for reasons that had nothing to do with geomagnetic storms or solar flares. On that date, a comet was reaching perihelion. The comet's designation is C/2026 A1, and it belongs to a family of objects called the Kreutz sungrazers, comets that dive extremely close to the sun's surface, sometimes passing through the corona itself. This family of sungrazers has a documented history. The Great Comet of 1843 was a Kreutz sungrazer that became bright enough to be visible in daylight. Observations recorded it reaching magnitude -2, or perhaps even brighter, bright enough that observers in the daytime sky could see it without optical aid. The Great September Comet of 1882 was another Kreutz sungrazer, discovered less than 4 months after its perihelion passage. These comets are fragments of a much larger parent body that was disrupted into smaller pieces that continue to follow nearly identical orbits that bring them to the same part of space near the Sun. When one passes near the Sun, others follow at intervals of decades or centuries, all following the same dangerous trajectory toward the fire. This particular comet, which goes by the Discovery designation maps, was scheduled to reach its closest approach to the Sun at 0.00573 astronomical units. For context, that's less than half the distance from Earth to the Sun. It means this comet would be passing through the region of space where the Sun's corona extends and where the solar wind is being accelerated outward by the immense magnetic and thermal forces near the Sun's surface. The corona extends outward from the photosphere, and the temperature of the corona is counterintuitively hotter than the surface below it, millions of Kelvin instead of thousands. The mechanisms that heat the corona are still not entirely understood, but what is understood is that the corona is where the solar wind originates, where charged particles are accelerated to speeds that carry them outward at hundreds or thousands of kilometers per second. We covered this comet in detail weeks ago on this channel, when the initial calculations suggested it might be visible to modern space weather satellites. The orbital prediction had changed several times, and so had the question of whether it would survive passage so close to the solar photosphere. By April 4th, the answer was becoming clear. The comet was going to complete its perihelion passage. It would emerge on the other side of the Sun, transformed, if it survived at all. And it would do so on the exact same date that geomagnetic conditions were expected to peak. What happens to a comet when it passes through the actual solar corona? The comet is composed primarily of frozen volatiles, water ice, carbon dioxide ice, methane ice, carbon monoxide ice, along with dust and silicate materials locked in that icy matrix. As the comet approaches the Sun, the solar radiation heats that icy nucleus. The surface ice sublimates, turning directly from solid to gas. The outgassing accelerates as the comet gets closer and the radiation becomes more intense. The coma expands. The tail stretches outward in the direction away from the Sun, pushed back by solar radiation and the solar wind. But if the comet actually passes through the corona, the temperatures climb into the millions of Kelvin. The ices don't simply sublimate. They catastrophically vaporize. The dust is entrained in the plasma. The nucleus, if it's small enough, can be heated and disaggregated. But something survives. Meteoritic material with higher vaporization temperatures persists. Metals persist. Silicates persist. And that material is moving at the perihelion velocity of the comet, which for the Kreutz sungrazer family is approximately 170 to 185 kilometers per second. At such speeds, the material doesn't gently disperse. It becomes high-velocity ejecta. On April 4th, another object was also making a significant close approach to Earth. Asteroid 2023 DZ2, a carbonaceous near-Earth object, roughly 30 to 60 meters in equivalent diameter, was scheduled to pass the Earth at a distance of 2.63 lunar distances. That means it would pass closer than the Moon without impacting the Moon, crossing through the interior of the Earth-Moon system. In terms of near-Earth asteroids and meteorite falls, that's a close approach by historical standards, though not dangerously so in terms of impact probability. The asteroid would be traveling at approximately 20 kilometers per second relative to Earth, a typical velocity for near-Earth asteroids. There is one more piece to this convergence, and it's the one that carries the most uncertainty and the most room for interpretation. On April 1st, the same day as the Artemis II launch, a fireball was detected by the Compendium of Nearby Exoplanet System Observations, or CNEOS database. CNEOS is a catalog maintained by Planetary Science Institute researchers who compile observations of bolides and fireballs detected by the Department of Defense's infrared satellites. This particular fireball released energy equivalent to 0.079 kilotons of TNT, which would place it in the upper tier of modern fireball detections. The velocity was listed as 37.3 kilometers per second, which is notably fast, faster than the typical near-Earth asteroid impact velocity, and closer to the speed that cometary material approaches Earth. Now, the caveat here is that CNEOS has documented accuracy problems. The coordinate reliability is variable. There was an entry on March 23rd that was off by 4,000 miles. The atmospheric entry location for the April 1st fireball sits in a region where validation is difficult. But when you're looking at the broader data structure, the statistical anomalies in fireball frequency that we documented in earlier research, you're seeing a thread of elevated activity that corresponds temporally with the other events we're discussing. This isn't causation. This is clustering. And clustering in the context of rare events demands attention because it violates the assumption of random distribution. The hypothesis under consideration is not that the comet caused the fireball or that the fireball is a fragment of the comet. The orbital mechanics don't support that, but rather that multiple populations of small bodies in the inner solar system are showing elevated activity simultaneously. Whether that's purely coincidental or whether it reflects some deeper structure in how material concentrates in our planetary neighborhood remains an open question. So on April 4th, 2026, the Artemis II crew would be transiting deep space during a G3 geomagnetic storm, or possibly a G2 that peaked toward the upper boundary of its category. The same date on which a Kreutz sungrazer comet reached perihelion just on the other side of the Sun. The same date on which an asteroid passed through the Earth-Moon system. The same date on which additional fireball activity might be occurring at an elevated statistical rate. Now, I'm not claiming causal connection. The comet is not causing the geomagnetic storm. The asteroid is not directing the solar wind. The fireball detections are not responding to the asteroid. But the temporal clustering of these events, each independent in its causation, each driven by different physical mechanisms, all converging on April 4th within a window of hours. That clustering is statistically unusual. And it's the kind of pattern that makes some people wonder whether there's something about how our solar system operates on rare occasions, some resonance or configuration that we don't yet fully understand. But here is what we do know is happening concurrently. The Earth itself is responding. In the early hours of April 2nd, seismographs across a region called the Molucca Sea, which sits in the complex plate boundary zone between the Pacific, Philippine, and Eurasian plates in Southeast Asia, began registering an unusual pattern of activity. The Molucca Sea plate collision zone is one of the most geologically complicated regions on Earth. The Pacific plate is subducting northward beneath the Philippine plate. The Philippine plate is simultaneously subducting eastward beneath the Molucca plate in what's called a double subduction zone, an unusual configuration where a small plate is being pulled down from both sides by larger plates converging around it. The stress that accumulates in such a region is substantial and complex. The fault planes are steep, the rock is brittle and fractured. Earthquakes are a normal part of the system's operation, but normal operation and unusual operation are separated by specific statistical thresholds. Over a span of approximately 12 hours, 23 earthquakes of magnitude 4.5 or greater were recorded. Within that cluster were several larger events, an M5.9 at a depth of 134 kilometers, an M5.8 at 89 kilometers depth, and an M5.6 at 114 kilometers. In earthquake terms, that's a significant swarm. The depth suggests these were occurring on the subduction zone interface itself, where the Pacific plate is grinding downward beneath the overlying geology. In that environment, even in that seismically active region, a swarm of this intensity and clustering in a 12-hour window was notable. The temporal overlap was striking. The G2 geomagnetic storm had arrived at precisely the time this swarm intensified. Now, seismologists will tell you, and correctly, that earthquakes are fundamentally driven by stress accumulated over geological timescales, released through plate motion and friction. The sun has nothing to do with it. Geomagnetic storms are electromagnetic phenomena occurring in the upper atmosphere and magnetosphere. They don't directly couple to the solid Earth in any mechanism that conventional tectonophysics recognizes. And yet, a body of research has emerged over the past decade suggesting that the correlation might not be pure coincidence. In 2020, researchers named Marchitelli and colleagues published a statistical analysis examining the relationship between periods of elevated geomagnetic activity and the occurrence of significant earthquakes. Their work found that during certain geomagnetic conditions, particularly elevated Kp indices and southward-pointing Bz components, there was a statistically significant increase in the probability of M5.6 and larger earthquakes occurring within a specific time window. The mechanism proposed involved ionospheric coupling and atmospheric electrical effects, but the details remained speculative. The ionosphere, the layer of the upper atmosphere where electrons and ions are concentrated, is sensitive to disturbances in the magnetosphere. During a geomagnetic storm, the ionosphere becomes more electrically active. Currents flow. Electric fields develop. Those fields extend downward through the mesosphere and into the stratosphere. Whether they extend deep enough to couple to the processes in the upper crust and influence earthquake triggering is the question. What wasn't speculative was the correlation itself, which survived multiple statistical tests and was replicated in independent datasets. The Molucca Sea swarm was occurring within the Russell-McPherson equinox window, which in 2026 would remain open through approximately April 20th. During this seasonal window, the geometry of the Sun-Earth system creates a condition where geomagnetic storms are more geo-effective and more likely to produce strong coupling to Earth's magnetosphere. The equinox windows occur in March and September of each year because of the specific orientation of Earth's magnetic dipole axis relative to the ecliptic plane. At equinox, the solar wind direction and the magnetosphere's orientation align in a way that creates maximum efficiency for energy transfer from the solar wind into the magnetosphere. Geomagnetic storms during equinox windows are stronger and more likely to penetrate deeper into the magnetosphere and ionosphere than at other times of year, and they may be associated with something else. Something that appears in the earthquake data as a temporal correlation that refuses to be explained away. Earlier in the year, when the Tonga region experienced an M7.5 earthquake on March 24th, a G3 geomagnetic storm had arrived just hours before. The seismic zone there is another subduction zone, another region where stress accumulates on the interface between plates. When Vanuatu experienced an M7.3 on March 30th, an X1.4 flare had erupted from the sun the day prior, with a CME arriving within hours. Now, in the Molucca Sea, an M5.9 had accompanied the arrival of a G2 storm. The thread was becoming visible, not causation, not mechanism, but sequence and statistical improbability that demanded acknowledgement. Meanwhile, above the Earth, the terrestrial atmospheric response to the geomagnetic storm was unfolding in real time. The National Weather Service had issued 436 separate weather alerts across the continental United States on April 2nd and 3rd. In Chicago and the surrounding region, tornado watches had been posted with reported wind gusts up to 70 miles per hour and hail as large as quarters falling from clouds that were rotating with dangerous intensity. In Louisiana, flash flood warnings were in effect for multiple parishes. The parishes most affected were those along the Gulf Coast, where moisture from the warm water was being driven inland by storm circulation. Rainfall predictions of 5 to 7 inches were falling in some areas in less than 6 hours, the kind of precipitation that produces life-threatening flooding, overwhelms drainage systems, and turns roads into rivers in minutes. 33 winter storm warnings stretched across the upper Midwest and Great Lakes region, from Minnesota to Michigan to New York. The snow accumulation predictions ranged from 6 to 12 inches, with some areas receiving higher amounts. That doesn't sound catastrophic until you realize that it was early April, that trees were already leafing out, that the added weight of wet spring snow on leafy branches causes branches to snap and power lines to fail. The combination of heavy wet snow and leaf-bearing trees is one of the most destructive weather scenarios in the temperate latitudes. 13 red flag warnings for fire weather had been issued for western and plain states, where relative humidity was dropping to 10% and sustained winds were gusting above 60 miles per hour. That combination, low humidity and high wind, creates the conditions for wildfire to spread at catastrophic rates. Fire that might be contained in normal conditions can become uncontrollable in such environment. And for Friday, April 4th, an enhanced risk for severe weather was being posted for Iowa and Missouri, with the potential for strong to severe thunderstorms and isolated tornadoes. That enhanced risk extends across an area containing several million people. The Earth's weather system, driven by solar radiation and atmospheric dynamics, was responding to the geomagnetic disturbance with increased instability. The volcanic monitoring networks were showing upticks as well. Kilauea in Hawaii was at USGS watch status with orange alert level for ash emissions. The volcano wasn't erupting, but it was becoming more restless. Seismic activity beneath the summit was increasing. Ground deformation was accelerating. Great Sitkin in the Aleutian Islands had also moved to watch status with orange alert. That volcano, too, was showing signs of increased activity. The whole terrestrial system, from the solid Earth to the atmosphere to the oceans, appeared to be oscillating at a higher amplitude than usual. And above it all, 4 astronauts continued their trajectory outward, toward the moon, into radiation and uncertainty. The measure that matters most for a crew traveling beyond Earth orbit is something called the proton flux, measured in particles per centimeter squared per second. On April 2nd, the greater than 10 mega-electron-volt proton flux had reached 4.72 particles per flux unit at the GOES spacecraft, with a peak reading of 5.52 pfu. The threshold for an S1, or minor radiation storm, is 10 pfu. The Space Weather Prediction Center was forecasting a 50% probability that the greater than 10 mega-electron-volt proton flux would cross that threshold on April 3rd and 4th. That would constitute an S1 radiation storm event. But the really significant number was the greater than 1 mega-electron-volt proton flux, which had reached 1,135.7 pfu, with a peak excursion to 3,488.3 pfu. That level is extremely elevated. For context, the greater than 2 mega-electron-volt electron flux was also expected to return to high levels on April 3rd and 4th. These are the particles that penetrate deepest into living tissue and pose the most significant acute radiation hazard to crew. High-energy electrons and protons passing through a human body interact with the cells, causing ionization, breaking chemical bonds, producing reactive oxygen species. At high enough doses, the damage accumulates faster than the body's repair mechanisms can handle it. Now, consider what different dose levels actually do to the human body. At 50 millisieverts, there is a measurable increase in long-term cancer risk, but no acute effects. At 100 millisieverts, acute radiation sickness becomes possible for some individuals. At 200 millisieverts, acute radiation sickness is likely, nausea, some vomiting, cognitive effects. At 400 millisieverts, mortality becomes significant without medical intervention. At 1,000 millisieverts, death is nearly certain. NASA's career dose limit for astronauts is set at 600 millisieverts of career effective dose, a threshold that balances the cancer risk against the benefits of spaceflight over a 40-year career. For a single mission, the guideline for acceptable dose is 90 millisieverts, which preserves a safety margin relative to the career limits. The historical reference point that haunts the minds of radiation safety officers at NASA is August 1972, between Apollo 16 and Apollo 17. A solar particle event of extraordinary magnitude occurred, catching neither crew in transit because of the particular timing of the Apollo schedule. The event was powerful enough that had a crew been in the middle of cislunar space during that event, the peak dose rate was 241 rem per hour. The cumulative dose during passage through the radiation zone was 358 rem, or in modern terminology, 3,500 580 millisieverts. Those numbers are in the range where acute radiation sickness becomes likely. Modern astronaut training includes awareness of what exposure to that level of radiation looks like. Nausea, potential vomiting, potential cognitive effects, and long-term cancer risk elevation. The 1972 event remains the largest single-day solar proton event documented in the space age. In the worst-case scenario, had the astronauts been in a spacecraft with limited shielding during that 1972 event, the mission might have become a medical emergency, requiring an immediate return to Earth with a potentially compromised crew. Current conditions on April 2nd and 3rd are 3 orders of magnitude below the 1972 event. But here's the complication. One X-class flare, one of the events that the forecasters were giving a 20 to 25% probability for the next 24 hours, could close that gap very quickly. The August 1972 event wasn't preceded by any obvious warning signs that would have allowed for immediate avoidance. Modern early warning systems are better, but they're also constrained by the speed of light and the practical limitations of reaction time. A crew in cislunar space has no abort capability. They cannot simply turn around and come home. The trajectory, the fuel, the momentum all make a hasty return impossible. They are committed. The Artemis II spacecraft, called Orion, does have some radiation shielding. NASA tested a specialized garment called the AstroRad vest on the uncrewed Artemis I mission that flew in December 2022. The vest was designed to protect the torso and core organs from radiation. It's constructed with hydrogen-rich material that provides additional shielding to the torso, material that was selected for its ability to moderate and absorb high-energy charged particles. Testing with anthropomorphic phantoms, test dummies named Helga and Zohar, showed the vest could reduce dose to the core body by a meaningful percentage, somewhere in the range of 20 to 40% for certain radiation energies. But it doesn't protect the extremities. It doesn't protect the head. It doesn't protect the lungs, or the eyes, or the areas that matter for vision and long-term function. And it's one layer of mitigation in a system that depends on multiple overlapping protections. Here's the other thing that nobody likes to talk about. The Artemis I mission, the uncrewed test, encountered damage to the heat shield during re-entry. The damage was unexpected. It was more severe than had been observed in ground testing or in any of the prior analysis. The cause was eventually traced to gaps in the material degradation simulation during development, and some unknowns in exactly how the thermal environment behaves during the actual re-entry trajectory. The heat shield is composed of an ablative material that is designed to burn away during re-entry, dissipating the immense thermal energy of entering the atmosphere. If the ablation isn't uniform, if there are gaps or voids in the material, the underlying structure is exposed to temperatures that exceed its design limits. NASA, in response, modified the heat shield design and conducted additional validation testing. But that validation testing was conducted on test articles and in computer simulations. It was never conducted in the actual re-entry environment of Artemis II itself. The risk is understood and formally accepted, but the gap between theoretical validation and operational demonstration exists, and it sits directly between the crew and the heat of re-entry. The gap between an acceptable risk in a spreadsheet and an acceptable risk when you're the person strapped into a capsule that's entering the atmosphere at 25,000 miles per hour is measured not in safety factors, but in philosophy. The timeline of the radiation hazard creates a window of acute risk. April 3rd and 4th are the critical days. If an X-class flare erupts before April 4th at midnight UTC, the CME arrives, the radiation storm peaks, and the crew is still in the region of space, where the magnetosphere is least protective. The crew's distance from Earth creates a geometry where they have effectively zero protection from the planet's magnetic field. After April 4th, They're entering a region where the solar wind begins to behave more predictably, where the probability of additional major eruptions begins to decline, where the cumulative dose they've received begins to represent a smaller fraction of acceptable limits. The gap between manageable risk and we need to seriously reconsider whether this crew is safe is measured in hours, not days. And that gap coincides exactly with the April 4th convergence. Let me be direct about the conspiracy angle, because it's worth taking seriously for a moment, even if we ultimately conclude it's overblown. The question being asked in certain online forums and specialized communities is simple. NASA knew about the deteriorating solar conditions and launched anyway. The evidence for this, such as it is, relies on data that is publicly available. The G1 watch was issued. The X 1.4 from region 4405 was measured on March 30th. The solar wind was elevated on the morning of April 1st. Coronal mass ejections were in transit. Active region positioning was geoeffective. A meteorologist at the Space Weather Prediction Center could have, and probably did, flag these conditions in the hours before launch. The response from NASA, were they directly asked, would be that launch commit criteria were met. The go-no-go decision for space weather uses specific thresholds established through decades of experience and validated through statistical analysis. At the moment of liftoff, those thresholds were not breached. The space weather envelope that was accepted as part of the mission design inherently includes some probability of geomagnetic disturbance during the mission window. By that logic, the decision to proceed was sound and defensible. But there's a softer version of the conspiracy hypothesis that's harder to dismiss. Schedule pressure is real. Political optics matter. A space program that has been promising lunar return for years faces intense scrutiny when launch dates slip. The cost overruns on Artemis have been substantial. The program has already run to well over $100 billion by some accounting methods when you include the development of the rockets and spacecraft and the support infrastructure. Every delay represents additional expense and political vulnerability. The space launch system itself, when you include all its development costs, comes to roughly $2 billion per flight. Another slip in the schedule means another delay and another $2 billion in opportunity cost. When the morning of April 1st arrives and weather is nominal and the forecast is uncertain and the probability of some level of space weather during the 9-day mission is high but manageable, does the conversation subtly shift toward launching? Does the threshold for risk acceptance, applied unconsciously but consistently, shift just slightly higher because the political cost of another delay is becoming untenable? I don't have access to the sealed go-no-go transcripts. I don't know what was said in those rooms. But I know that institutions, even careful ones, operate under pressures that aren't always quantifiable and that sometimes aren't even consciously acknowledged. History provides sobering precedent. The Challenger disaster in 1986 was preceded by engineering recommendations that the shuttle not launch in cold weather. The temperature at launch was 36 degrees Fahrenheit. The solid rocket booster O-rings, which were designed to seal the joints in the booster, became brittle at cold temperatures. An engineer named Roger Boisjoli specifically recommended not launching. The recommendation was overridden. The mission proceeded. 73 seconds after launch, one of those O-rings failed, allowing hot gases to escape, leading to structural failure of the external tank and the orbiter, resulting in the loss of the spacecraft and the crew. Years later, in examining the decision, NASA investigators concluded that schedule pressure and political pressure to launch had influenced the risk acceptance process. People knew the risk. People articulated the risk. But the pressure to launch overrode the caution. Columbia broke apart on re-entry in 2003, again from damage that had occurred at launch. A piece of foam insulation had broken away from the external tank and struck the leading edge of the orbiter's left wing. It was a known vulnerability of the external tank. Foam shedding had happened on previous flights. But the risk was accepted because it had never caused a mission-ending catastrophe. Columbia was damaged. The damage went undetected. The crew was unaware of the vulnerability. During re-entry, the wing leading edge, already weakened, failed. Hot gases from re-entry penetrated the wing structure. The orbiter came apart. 7 people died. The investigation that followed examined, among other things, whether the knowledge of foam shedding vulnerability, combined with the ability to potentially inspect or mitigate the damage, should have led to a different decision process. The conclusion was nuanced. The institution had normalized the risk. Risk that should have been treated as exceptional had become routine, had become accepted, had become the baseline assumption against which other missions were planned. There's another angle to the conspiracy thinking, and this one concerns the Artemis I heat shield damage. The fact that uncrewed test vehicle encountered damage that was larger than anticipated, and that the subsequent fix has never been tested in an actual operational re-entry scenario, sits in a space of legitimate concern. It's not a scandal. It's not a cover-up. But it is a gap between the controlled environment of testing and the actual environment of operation. Heat shields matter. They matter in ways that are visceral and immediate. If the Artemis II re-entry encounters unexpected damage, if the heat shield develops cracks or ablation that exceeds the design margins, the crew would face a potentially catastrophic situation with limited options for response. NASA has accepted this risk as an appropriate trade-off given the maturity of the design and the analysis that supports it. But the acceptance of risk is not the elimination of risk. And then there's the interpretation that sits in the realm of speculative, but not entirely implausible. The Chejevsky hypothesis, formulated by a Russian biophysicist in the early 20th century, proposed that solar activity cycles have measurable effects on biological systems, including human behavior and disease patterns. Mainstream science dismissed this as unsupported. But in recent years, some researchers have found correlations between solar activity and markers of human physiology, from heart rate variability to circadian rhythm disruption. The hypothesis remains deeply controversial. But the April 4th convergence, the CME, the comet, the asteroid, the earthquake swarm, the geomagnetic storm, the weather disruption, creates a moment when the entire Earth system is being driven by solar input in ways that are visible at every scale. Some observers are interpreting this as a cosmic warning, a signal that the solar maximum of this cycle is reaching a phase where the boundary between controlled system, behavior, and chaotic behavior is becoming thin. What NASA actually isn't saying, or at least isn't saying loudly, is that the Artemis II crew is operating at the frontier of our understanding of safe human operation in the space environment. We've stayed in low Earth orbit for 50 years, where the magnetosphere provides constant protection. Artemis II is the first time in 53 years that we're inserting human beings into the region of space where that protection fails. If the radiation measurements come back elevated, if the crew experiences any effects during re-entry, if the heat shield shows damage, NASA will face questions about whether the program can proceed with Artemis III, which will place crew on the lunar surface with even less protection. The lunar surface has no atmosphere, no magnetic field, no protection at all from space weather. The radiation environment at the moon is substantially harsher than in cislunar transit. The political and programmatic implications of a "we need to reconsider" moment are substantial. There's also the fact that the SMILE mission, the Solar Wind Magnetosphere Ionosphere Link Explorer, is scheduled to launch on April 9, 2026. SMILE is a collaboration between the European Space Agency and the Chinese Academy of Sciences, and it's designed specifically to study the interactions between the solar wind, the magnetosphere, and the ionosphere, the exact mechanisms that might explain why the April 4th convergence looks so unusual. SMILE will carry instruments that measure the magnetosphere and the interaction region where the solar wind meets Earth's magnetic field. It will provide data about the exact physical processes that connect solar activity to atmospheric and geomagnetic responses. The timing is suggestive. 1 week after the Artemis II crew has transited through the zone of maximum risk, the scientific mission to understand that exact zone will lift off. In an alternate timeline, one might expect that mission to launch earlier, to provide data that informs the Artemis II decision. But that's not how timelines work. Science operates on its own schedule. Missions take years to develop. Launch windows are narrow. SMILE comes after Artemis II because the universe didn't arrange for it to come before. We are now in the window. April 3rd and April 4th are the inflection points for the Artemis II mission. Every hour that passes without an X-class eruption from one of the 3 geo-effective active regions is a good hour. Every hour that passes without an unexpected eastward shift in the interplanetary magnetic field direction is a good hour. The regions that could produce a major solar eruption are still there. Region 4405 is still rotating, still facing Earth, still carrying the magnetic complexity that makes M-class and X-class eruptions possible. Region 4404 just erupted with an M3.5. Region 4409 is still positioned to produce significant activity. The probability isn't negligible. It's measurable and real. And yet, the overwhelming probability still favors mission success and crew safe return. The crew will almost certainly come home. The statistics support this. The forecasts support this. The historical record of cislunar missions supports this. Statistically, what we're witnessing is the normal operation of probability. Extreme events are rare, and Artemis II, even with the elevated space weather conditions, sits within the envelope of acceptable risk that NASA calculated and accepted. But what they bring back will matter. The dosimetry data from the Orion spacecraft's radiation monitors will be scrutinized with intense attention. Every dose reading, every exposure measurement, every radiation event detected during the mission will be analyzed in detail. If the data shows that crew received elevated dosimetry, but remained within acceptable limits, NASA can move forward to Artemis III with confidence. If the data shows something unexpected, something that suggests the shielding or the trajectory planning needs revision, then the program faces harder decisions. Artemis III, planned for late 2027, will place crew on the lunar surface itself. The lunar surface has no atmosphere, no magnetosphere, no magnetic protection at all. The radiation environment there is harsher than in orbit, harsher than in cislunar transit. If Artemis II data suggests that cislunar transit during active solar conditions is more hazardous than calculated, then the question of whether we're ready to put humans on the moon becomes more complicated. History provides the precedent. August 1972 saw the single most significant solar particle event of the entire space age. No crew was in transit, but the event was documented in detail. The parameters were measured. The lessons were learned. The solar energetic particle event was analyzed. The physics was understood as completely as possible. When Apollo resumed after that event, the program didn't stop. The risk was understood and carried forward. NASA adjusted operations, modified procedures where possible, and continued. The missions flew. The astronauts returned safely. And 50 years later, we're at a moment where another generation is pushing back into that same realm of uncertainty. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen are 4 highly trained astronauts who have spent years preparing for this mission. They understand the risks. They have trained in simulators and in neutral buoyancy pools and in centrifuges and in classrooms. They have committed their careers to the understanding that space exploration operates at a frontier where risk cannot be entirely eliminated, only managed and accepted. Wiseman has flown twice to orbit before, commanding complex spacecraft operations in the unpredictable environment of space. Glover has tested experimental aircraft at the edge of the flight envelope, understanding the mechanics of controlled risk in extreme environments. Koch has spent more than 1,000 hours in orbit. Hansen has spent years as an astronaut in training, preparing for exactly this moment. These are people who have chosen this path with full knowledge of the stakes. They're trusting their training. They're trusting the spacecraft. They're trusting the engineers who design the systems. They're trusting the forecasters who predict space weather. They're trusting the science that says the statistics favor their return. They're also trusting something harder to quantify: the institutional memory of decades of spaceflight, the lessons learned from every near miss and every tragedy, the understanding that reaching beyond the safety of low Earth orbit requires accepting uncertainty while maintaining the rigorous discipline that keeps that uncertainty manageable. And right now, they're traveling into a region of space that very few humans have ever visited, following a trajectory that has been calculated and validated, carrying equipment that has been tested and refined toward a destination that humanity has not approached with a crew in place in more than 5 decades. The real question that drives this mission isn't, can we fly to the moon? We know we can. Apollo proved that in 1969. The question that Artemis II is answering is far more subtle and more profound. Can we do it in the age of real-time global monitoring and open data? Can we do it with full understanding of the hazards, with open eyes toward the risks, with mitigation strategies that work because they're based on science and engineering rather than fortune? Because right now, 4 astronauts are heading further from home than any human in 53 years. Behind them, Earth is growing smaller. Ahead of them, the moon waits. And between them and home is a region of space where the sun is at its most active, where a comet is diving toward perihelion, where an asteroid is passing through our cosmic neighborhood, where earthquake swarms are clustered across the planet, where a G3 geomagnetic storm is approaching its peak. The CME is on its way. The radiation window is narrow, and all of it converges on April 4th. The families of these astronauts are watching. The space program is watching. The world is watching. Luck is exactly what this mission needs, and luck is the one thing that science cannot entirely control. And that's the question we're asking right now, in real time, as the solar system rearranges itself around 4 people in a spacecraft hundreds of thousands of kilometers from home. This story is developing in the hours right now. We'll continue following it as it unfolds. This is The Quiet Archivist.